Hi everyone, my name is Abner Zárate and I'll be presenting my poster that's named Divalent Metal Substitution on Magnesium and Aluminum Ternary Layer Double Hydroxides and its effect on their absorption properties. It is presented at the SC3 Symposium of the 30th International Materials Research Congress. Starting with a little introduction, it's well known that water is essential for life. Human health, settlements, energy production, industrial development, economic growth, and ecosystems depend on it, and therefore on its availability, which is linked to its quality, since its contamination can exclude different uses. One of the main sources of water pollution are dyes, which usually reach bodies of water through industrial discharge. It's due to the effects that this can have on ecosystems and living beings that the development of innovative materials that allow their efficient removal from water bodies is imperative. This is where the layer double hydroxides, or LDH, come in. These are inorganic clays whose structure is based on octahedrons with metal ion cores, where the substitution of a divalent cation for a trivalent one results in positively charged layers, which leads to the formation of interlaminar galleries with solvent and anions to counteract the charges. It's due to their properties that they can be used in many different fields, including the absorption of anionic dyes, such as Congo red. Recent investigations show that if we substitute part of the metal ions with others of the same nature, we can improve the material's properties. This is why we could propose a method to synthesize cobalt, nickel, copper, and zinc substituted magnesium and aluminum ternary layer double hydroxides with enhanced adsorption properties, compared with the binary material. To do so, we first selected the doping molar ratios to work with. Then we made different solutions containing the metal ions and added urea, all using a solution of ethylene glycol as solvent. We took said solution and subjected them to the radiation of a conventional microwave. We then separated and dried our products to then disperse them in methanol, and then carry out a series of electrophoretic deposition. Lastly, we took the deposited materials and executed a series of absorption processes using Congo red as a study model. As the results, we first present the FTIR spectra. Each quadrant corresponds to a substitution metal: cobalt, nickel, copper, and zinc, all compared against the reference material. Comparing the spectra with the ones on the literature, it is verified that they partially coincide with those reported for LDH with ethylene glycol intercalated in the interlaminar galleries. Now we present the X-ray diffraction patterns of the materials. We can appreciate that they all show the same peaks than the hydrotalcite, mineral against which LDH are often compared. The minor displacements are due to the chemical differences between the mineral and the substituted materials. We notice how the materials substituted with cobalt, nickel, and copper show only the crystalline phase of the LDH, while the materials substituted with zinc show other phases. This is why we decided to only continue working with the first three metal ion substitute. Lastly, we present the result from the adsorption test. At the beginning of the process, all the substituted materials have a slope greater than that of the reference material, which implies that the substitution increased the adsorption rate until equilibrium was reached. It is also noted that for two metal ion substitutes, nickel and copper, at least one of their materials exhibited higher adsorption than the reference material at equilibrium. All this allows us to confirm part of our hypothesis that LDH with transition metal ions as substituents have improved absorption properties. As the conclusion obtained from this work, we conclude that the cobalt, nickel, and copper substituted magnesium and aluminum ternary layer double hydroxides were obtained through a microwave-assisted synthesis. The appearance of the XRD peaks and IR absorption bands corresponding to an LDH indicate an incorporation of the doping metals in the material. On the other hand, zinc substituted magnesium and aluminum ternary LDH cannot be obtained in pure phase with this methodology. We also conclude that the substitution of the magnesium and aluminum LDH with a third divalent metal ion, specifically cobalt, nickel, and copper, enhance the absorption properties of the materials. However, further research is required to better understand the behavior of the adsorption properties enhancement. And that's it for this poster presentation. If you have any doubt regarding this investigation, feel free to contact me through my email. Thanks for listening.